Every model you have ever seen of the outer solar system is leaving something out, not the planets themselves, not their distances. What it leaves out is what Neptune actually is. In 1989, a spacecraft called Voyager 2 arrived at Neptune after a 12-year voyage. It had 4 hours to observe the planet before its trajectory carried it past and into deep space, never to return. In those 4 hours, it measured wind speeds of 1,500 kilometres per hour. The fastest hurricane ever recorded on Earth peaked at 345 kilometres per hour. Neptune's winds move at more than 4 times that speed, on a planet receiving less energy from the Sun than a candle held 3 kilometres away. 1,500 kilometres per hour, sustained, planet-wide, and that is just the wind. What Voyager found in those 4 hours violated every expectation that preceded it. The wind speed, the storm, the magnetic field, the moon in retrograde orbit. Every layer of Neptune that Voyager measured was wrong in a way the models had not predicted. This is a world we have visited once, for 4 hours, 35 years ago. Almost everything it showed us still does not have a complete explanation. Tonight we go through every layer. Start with the rule: weather requires energy. This is not a tendency with exceptions. It is the operating law of every planetary atmosphere we have ever studied. Without a source driving temperature differences, there is no circulation, no wind, no storm. The atmosphere sits cold and still. Energy in, weather out, direct and measurable. On Earth, that energy comes from the Sun. The Sun heats the equator more than the poles. It heats land faster than ocean. It heats the lower atmosphere differently from the upper. Every one of those uneven heating patterns creates a temperature gradient, and temperature gradients do not stay still. Warm air rises. Cool air rushes in to replace it. The pressure difference becomes wind. The wind interacts with the planet's rotation, with the ocean surface, with mountain ranges, and the result is hurricanes, jet streams, blizzards, and every breeze you have ever felt through an open window. All of it, without exception, traces back to sunlight landing unevenly on a surface. This is not unique to Earth. Mars receives about 43% of the sunlight Earth does, and its atmosphere is accordingly thinner and less active. Jupiter receives only about 4% of Earth's solar input, but supplements it with substantial internal heat, producing weather systems visible from amateur telescopes. Saturn, Uranus, every world we have studied, energy input determines atmospheric activity. More energy, more weather. Less energy, less weather. The rule holds across every case in the dataset. Now apply it to Neptune. Neptune orbits the Sun at roughly 30 astronomical units. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometres. At 30 times that distance, the Sun's energy is spread outward following the inverse square law. The total solar energy radiates outward from the Sun in all directions, diluting as it covers an ever-expanding sphere. At 30 times Earth's distance, that sphere is 900 times larger in surface area. Every square metre of Neptune's upper atmosphere receives 1/900th of the solar energy that every square metre of Earth's upper atmosphere receives. 1/900th. Let that become concrete. At Earth's solar input, the atmosphere can sustain hurricanes at 345 kilometres per hour across ocean basins, jet streams circling the entire planet at altitude, and thunderstorms reaching from the surface to 15 kilometres above it. Neptune's atmosphere receives less than 1% of that energy input. By the physics that connect solar input to atmospheric dynamics on every other planet we have studied, Neptune should have winds of a few kilometres per hour at most, something barely worth measuring. The atmosphere should be nearly still, its faint movements too gentle to resolve from any Earth-based telescope. Neptune gets almost no sunlight and has the fastest winds in the solar system. 1,500 kilometres per hour, more than 4 times the fastest hurricane ever recorded. More than 40% of the speed of the SR-71 Blackbird, which at 3,540 kilometres per hour was the fastest air-breathing aircraft ever built. On a planet where the sun, seen from the cloud tops, is not a warm, face-filling disk but a very bright star, stripped of the authority you associate with the sun. The numbers do not work. Not by a narrow margin that some atmospheric feedback mechanism might close, by a factor of hundreds. The 1,500 kilometres per hour is not slightly more than the models predict. It is categorically outside what the available solar energy can produce, regardless of how the atmospheric physics is parameterized, which means the energy is coming from inside the planet. Voyager confirmed what faint pre-visit thermal observations had hinted. Neptune radiates approximately 2.6 times more energy into space than it receives from the Sun. More than half the energy powering Neptune's atmosphere is not solar. It is internal. It rises from inside the planet. Where does that heat come from? Neptune is still cooling from its formation. When the solar system assembled from a collapsing cloud of gas and dust 4.5 billion years ago, the process was violent. Enormous quantities of material crashed inward under gravity, converting gravitational potential energy into heat. Planets did not form cold. They formed hot, heated by the violence of their own assembly. Jupiter and Saturn are still releasing this formation energy today. Both radiate more heat than they receive from the Sun. Neptune is doing the same thing, still warm from a birth that happened before Earth had formed, before any surface in the inner solar system had cooled enough to leave a geological record. That ancient warmth rises through Neptune's interior by convection, warmer material ascending, cooler material descending, circulation establishing itself along temperature gradients. As the heat reaches the deep atmosphere, it creates temperature differences far larger than the faint sunlight alone could produce. Those differences feed into the atmospheric circulation. The circulation amplifies them into the jet streams visible at the cloud tops. In the time it takes to sleep through a full night, 8 hours, Neptune's atmosphere moves approximately 12 million kilometres. Voyager took 12 years to travel the 4.5 billion kilometres from Earth to Neptune. Neptune's wind covers the same distance in less than 5 years, without propellant, driven purely by heat left over from an event 4.5 billion years in the past. The energy paradox deepens when you look at Uranus. Uranus is Neptune's nearest companion in the solar system, nearly identical mass, nearly identical radius, nearly identical bulk composition. If formation heat explains Neptune's excess thermal output, Uranus should behave the same way. It does not. Uranus radiates only about as much energy as it receives from the Sun. No detectable internal heat source. 2 planets that look nearly identical from the outside. One releasing formation energy at a rate sufficient to power the fastest winds in the solar system. The other cold and comparatively still. Nobody has a fully satisfying explanation for this. The leading hypothesis involves Uranus's extreme axial tilt of 98 degrees, a tilt consistent with a large early impact. That collision might have disrupted Uranus's internal convective structure, creating density layers that trap formation heat rather than allowing it to rise. Neptune, without evidence of such an impact, may retain unimpeded convection, allowing its formation heat to flow freely outward. It is a coherent hypothesis. It is not confirmed. Confirming it would require direct sampling of both planets' interiors, which no mission has ever done, and which no mission currently in development is designed to do. The data set available to test the hypothesis consists, for Neptune, of 4 hours of Voyager observations from 1989. What is confirmed is this. Neptune is a machine running on energy from 4.5 billion years ago, and that energy produces the fastest sustained winds in the solar system on a planet that the sun barely illuminates. A world that should be still, and is not. A world powered by the echoes of its own creation, still running, still chaotic, still only partially explained. The wind is only the first thing that does not make sense. Consider what the Uranus comparison demands from any proposed explanation. These are not merely similar planets. Their masses differ by about 5%. Their radii differ by about 3%. Their bulk densities are within a few percent of each other. Their atmospheric compositions belong to the same category. If formation energy were releasing differently in the two planets based on some standard cooling process, the difference would need to come from an internal structural difference that all external measurements have so far failed to distinguish. The two planets look nearly identical from the outside. Their internal heat outputs are dramatically different. Resolving this would require measuring the detailed internal density profiles of both planets through precise gravitational mapping from orbit, combined with thermal emission measurements in spatial detail, fine enough to determine whether the heat escapes uniformly or from specific regions. For Neptune, that mission does not exist. For Uranus, it is in early development with uncertain funding. The question of why two nearly identical planets behave so differently in this one critical respect is open, and it is likely to remain open for decades. What that means in practice is that the foundation of our understanding of Neptune's wind speeds is itself not fully explained. We know the wind speed. We know it requires internal energy. We know the internal energy exists. We do not know with complete confidence why Neptune has it and Uranus does not. The atmospheric model for the most chaotic planet in the solar system rests on a foundation that still has an open question at its base, and the wind is only the first layer. To feel the scale of the violation more precisely, consider what 1/900th of Earth's solar energy actually represents in watts per square metre. Earth's sun delivers about 1,361 watts per square metre to the top of the atmosphere. 1/900th of that is approximately 1.5 watts per square metre, arriving at Neptune's cloud tops. A single LED nightlight consumes about 4 or 5 watts. The total solar energy arriving at every square metre of Neptune's upper atmosphere is less than what a nightlight would consume. From this, Neptune is supposed to derive all of its atmospheric dynamics. Against that energy budget, 1/500 kilometres per hour is not just impressive. It is physically incoherent if you try to explain it using solar input alone. The internal heat that closes the gap is real and confirmed, but the energy accounting still has open terms. The total internal heat output, combined with the solar input, does not fully account for the observed wind speeds in all the atmospheric models that have been constructed. The energy budget has been partially closed by the discovery of internal heat, but not completely. Part of what makes this so difficult to study from Earth is the distance. At 30 astronomical units, Neptune presents an angular diameter so small in a telescope that, before Voyager, it appeared as a featureless blue disk in even the best ground-based instruments. No surface features were resolvable. The thermal output could be measured through infrared observations, the excess heat confirmed, but nothing about the internal heat source's structure or spatial distribution could be determined from that distance. After Voyager, the situation improved only marginally. Hubble could resolve some cloud features, and ground-based observatories with adaptive optic systems could occasionally track bright clouds. But none of these instruments can see below the cloud tops, probe the thermal structure of the deep atmosphere, or map the internal heat distribution. The picture built from all available data is of a planet substantially more energetic than its solar distance would predict, powered by something ancient and still incompletely characterized, observed in close detail for 4 hours. Everything that follows, the storms, the magnetic field, the captured moon, flows from this. A world that should be still and is not, powered by the echoes of its own violent creation, still running, still chaotic, 4.5 billion years on. One more way to feel the scale of 1,500 kilometres per hour. Compare it to the fastest things humans have built and launched into the sky. The space shuttle, at orbital velocity, moved at about 28,000 kilometres per hour. That speed requires rocket engines, external fuel tanks carrying hundreds of tons of propellant, and a thermal protection system to survive re-entry. It is the fastest speed any vehicle carrying humans has ever sustained in any atmosphere or near atmosphere. Neptune's wind moves at about 5% of shuttle orbital velocity. That does not sound impressive until you consider that shuttle orbital velocity is achieved by a rocket burning propellant at a rate of tons per second, and Neptune's wind maintains its speed across an entire planet, continuously, with no propellant, no engine, no combustion. Just heat rising from a planetary interior, 4.5 billion years old. The comparison also reframes what 345 kilometers per hour means for Hurricane Patricia. Patricia was the most powerful tropical cyclone ever recorded. It drew energy from an exceptionally warm patch of ocean surface, concentrating heat and moisture into a system that briefly reached sustained winds of 345 kilometers per hour. It required specific ocean temperature conditions, specific atmospheric humidity, specific interaction with the planet's rotation. It was, by Earth standards, an extreme and unusual event. At Neptune, 345 kilometers per hour would not be a storm. It would not be a notable wind speed. It would be a calm period. The 100 kilometers per hour that Voyager measured is not Neptune's peak. It is Neptune's normal. It has been Neptune's normal since before Earth had oceans, and it shows no sign of declining on any timescale that any current or planned scientific instrument will be able to observe. The comparison with any other atmospheric phenomenon on any other planet reinforces the same point. Earth's most powerful sustained wind systems, the polar vortex and the subtropical jet streams, move at between 200 and 400 kilometers per hour in their most intense states. These systems drive the weather experienced by billions of people and are the subject of intensive scientific study. Neptune's equivalent systems move at speeds 4 to 8 times greater, are sustained across an entire planetary circumference more than 12 times larger than Earth's, and are powered by an energy source whose full accounting has not been completed. The discipline that would be needed to fully describe and predict Neptune's atmospheric dynamics has not yet been developed, because the observational foundation for it does not yet exist. The wind speed is the number that defines Neptune because it is the number that concentrates every contradiction about the planet into a single measurement. Too fast for solar energy alone. Too fast for any structure to survive. Too fast for any storm to persist. Too fast for the atmosphere to organise into the stable patterns that would make the planet easier to understand. 1,500 kilometers per hour is not just Neptune's most extreme property. It is the property that makes every other property harder to study, harder to model, and harder to explain. Voyager 2 launched on August 20th, 1977. 3 days earlier, Elvis Presley had died. Jimmy Carter had been president for 7 months. The first home computer kits were just beginning to appear in hobbyist catalogues. There was no internet, no GPS, no mobile phone network. 12 years later, in August 1989, the Berlin Wall was still standing, though it would fall 3 months later. The Soviet Union was in its final years. The personal computer had become a fixture in offices and homes. Scientists who had designed Voyager were 12 years older. The youngest researchers looking at the arriving data had been children when the spacecraft left Earth. None of that time felt short. 12 years of flight, 4.5 billion kilometres, and then a window of 4 hours. Voyager was moving at roughly 61,000 kilometres per hour relative to Neptune. There was no option to slow down, no mechanism to enter orbit, no second pass. The spacecraft would swing through Neptune's vicinity at that speed, instruments running continuously, data radioed back toward Earth at the speed of light, taking another 4 hours to arrive given the distance. Scientists at JPL were receiving the first close images of Neptune at almost the same time the spacecraft was completing its closest approach, across a distance so vast that light needed 4 hours to cross it. The trajectory was engineered years in advance. It had to allow a close approach to both Neptune and its largest moon Triton within the same brief window. The geometry of the flyby, the speed of the spacecraft, the orbital positions of Neptune and Triton all had to converge in a specific configuration. The margin for error was small. There was no option to try again. In those 4 hours, every measurement that has defined our scientific understanding of Neptune for the following 35 years was collected. What the cameras showed first was colour. Neptune is a deep, vivid blue, distinctly richer and darker than Uranus's paler blue-green. The colour comes from methane gas in the upper atmosphere, which absorbs red and orange wavelengths from the faint sunlight and reflects blue wavelengths back into space. The colour had been predicted from spectroscopic observations made with ground-based telescopes. Predictions and photographs are not the same thing. The actual image of this completely blue world, with active cloud structures moving across its face, produced something that no model had prepared anyone for. Across that blue surface, cloud structures were moving. Long white streaks elongated by the wind into thin bands. Bright compact features appearing to be convective cells, regions where gas was rising rapidly from warmer atmospheric layers below and condensing into visible cloud at higher altitude before the jet streams caught and stretched them, and in the southern hemisphere, a feature so large it was immediately visible from Voyager's passing distance. They called it the Great Dark Spot. It was roughly 13,000 kilometres across. The Earth is 12,742 kilometres in diameter. The storm was larger than this planet. The fastest wind ever recorded on any planet runs on almost zero fuel. The jet streams flanking the Great Dark Spot were where Voyager registered its peak measurements, 1,500 kilometres per hour. To feel what that means, hold the SR-71 Blackbird in mind. It flew at 3,540 kilometres per hour, the fastest sustained flight in atmosphere ever achieved by any aircraft. Its design was an engineering response to the consequences of moving at that speed in air. Titanium airframe because aluminium would soften from aerodynamic heating. Specialized fuel that would not ignite at conventional engine temperatures. Nitrogen-filled tyres because the heat of takeoff would combust air or rubber. Hull panels that expanded so much from heat that the aircraft leaked fuel on the ground and had to reach operating speed before the metal sealed itself. The SR-71 represents the ceiling of what human engineering has pushed atmospheric flight to. Neptune's jet streams move at 42% of the SR-71's top speed. Not during a record attempt, not in a brief test, as the ordinary, continuous planet-wide baseline atmospheric circulation, powered by heat left over from a formation event 4.5 billion years ago. A structure placed in Neptune's jet stream would not be damaged. The kinetic energy of air molecules at 500 kilometers per hour would not knock the structure over in the way a hurricane knocks over trees. It would ablate the surface at a rate that would reduce reinforced concrete to particles within seconds. The particles would be swept thousands of kilometers downwind before they could settle. Nothing ever built is designed to exist in conditions remotely approaching this. Nothing ever built would survive this even for a moment. Voyager also photographed a smaller, brighter cloud cluster near the Great Dark Spot that scientists quickly nicknamed Scooter. It was moving faster than the storm itself, lapping it every few days, carried along in the jet stream at a pace that would take it from one side of Neptune to the other in about 2 days. A cloud cluster circling a planet with a circumference of 150,600 kilometres in 2 days. The speed was not exceptional for Neptune. It was simply the background atmospheric flow doing what it always does. Wind at Neptune does more than move atmosphere, it moves heat. Neptune's jet streams function as a planetary scale thermal mixer. The temperature profile across Neptune's surface is surprisingly uniform despite different latitudes receiving different amounts of the already faint sunlight. The jet streams carry thermal energy from warmer regions to cooler ones, faster than any gradient can accumulate. The warmth rising from the interior does not pool at one location. It enters the circulation and is distributed across the entire planet. This redistribution is a closed loop. Internal heat drives convective temperature differences. Temperature differences drive circulation. Circulation distributes heat and creates new temperature differences that sustain the circulation. The loop runs continuously. It has been running for 4.5 billion years. It will continue until the internal heat source, finite and slowly depleting, weakens enough that the loop can no longer sustain itself. That day is so remote that the sun will have exhausted its hydrogen fuel and altered or consumed the inner solar system before Neptune's winds meaningfully subside. The 500 km/h Voyager measured in 1989 is the current reading from a machine powered by formation energy, slowly spending itself since before Earth existed. The reading was taken once, it has not been checked since. The 4 hours produced one number, 1/500 km/h, and that number violated every expectation planetary science had built for the outer solar system. But the wind was not the only violation. Above the jet streams in the cloud pattern swept along by them was something that looked familiar and turned out to be nothing of the kind. The 4 hours at Neptune produced data that scientists are still working through today. The magnetic field measurements from that single transit have been the foundation for every theoretical model of ice giant dynamos developed since 1989. The wind speed measurements from those 4 hours remain the only direct confirmation of the atmospheric dynamics at Neptune. The images of Triton's surface taken during the same encounter are still the highest resolution close-up photographs of that moon in existence. There is something worth sitting with in the fact that a spacecraft designed in the 1960s and built in the 1970s, travelling for 12 years to a target that nobody had ever seen in close detail, produced a dataset that is still the primary source for understanding one of the most chaotic worlds in the solar system 35 years later. The spacecraft carried instruments that are, by current standards, primitive. The camera resolution was low by any modern measure. The data transmission rate was a tiny fraction of what any contemporary satellite uses. The onboard computer had less processing power than a present-day digital watch, and yet the data collected in those 4 hours has supported 3 decades of scientific work and still has not been exhausted. This is partly because the instruments were designed specifically for the task, and partly because of how little has been done to supplement those observations in the time since. The Voyager data has not been fully understood, in the sense that researchers continue to find new ways to analyse it as theoretical tools improve. But the data itself is finite. The questions it raises are not. There are questions about Neptune that the Voyager data cannot answer, that cannot be answered from Earth orbit, that cannot be answered by any telescope currently in operation or planned. They require proximity. They require time. They require going back. In the time it takes to fall into a full night's sleep, 8 hours, Neptune's atmosphere moves roughly 12 million kilometres. While you sleep, the jet streams cover a distance greater than the distance from Earth to the Sun. Voyager spent 12 years travelling to Neptune. Neptune's wind would cover the same distance in less than 5 years, without any propellant, without any machine, running continuously on energy stored since the planet's formation. The machine measured that wind in 4 hours, and the measurement has not been checked since. What those 4 hours actually measured in terms of the instruments operating and the data they returned is worth understanding in some detail. Voyager's narrow-angle camera had a resolution sufficient to image features roughly 5 kilometres across at Neptune's surface, provided the features persisted for the duration of an exposure. The wide-angle camera captured broader context. The cameras cycled through a series of colour filters, building up information that would allow the composition and reflectivity of cloud structures to be inferred. The photopolarimeter measured how light reflected from Neptune was polarized, giving information about particle sizes in the atmosphere. The ultraviolet spectrometer characterized the upper atmosphere composition. The infrared instrument measured thermal emission, confirming the excess internal heat output. All of this in 4 hours, while the spacecraft moved at 61,000 kilometers per hour relative to the planet. The imaging geometry changed continuously. Features in view at closest approach were no longer in view minutes later. The optimum window for close imaging of Triton occurred at a specific time in the flyby geometry. The magnetometer made measurements continuously along the trajectory, but the trajectory was a single arc through the magnetosphere, not a comprehensive survey. The plasma instrument measured the solar wind interaction at the specific approach geometry of August 1989. Each instrument captured what the geometry of a single hyperbolic flyby permitted. No instrument was able to make repeated measurements of the same feature or the same location at different times. The dataset is high quality within its constraints, and those constraints are severe. The scientists who designed Voyager knew this. The mission was designed as a flyby survey, a first look at worlds that had never been seen up close. The plan was always that a first look would be followed by dedicated orbital missions, as happened at Jupiter, Saturn, and eventually Mars. The plan did not account for the possibility that the first look at Neptune would remain the only look for decades. In 1977, when Voyager launched, nobody anticipated that Neptune would still be waiting for a follow-up mission 35 years after the initial flyby. The gap between Voyager and whatever comes next is not what anyone planned, it is what happened. In the years since Voyager's departure from Neptune, every other major target in the solar system has received additional visits. Mars, Jupiter, Saturn, and their major moons have all been studied by dedicated orbiters that arrived years or decades after the initial flybys and transformed the initial pictures into comprehensive scientific portraits. The flyby is the reconnaissance mission. The orbiter is the campaign. For Neptune, the reconnaissance mission was completed in 1989, and the campaign has not begun. The flyby picture is still the full picture. The reconnaissance is still the only data we have. There is a version of this story in which Voyager was the beginning of a program of exploration at Neptune, in the same way that Mariner 4's flyby of Mars in 1965 was the beginning of a program that eventually sent orbiters, landers, rovers and helicopters to the Red Planet. In that version, the 4 hours of Voyager data prompted a Cassini-class orbiter in the 2000s and a Neptune equivalent of the Curiosity rover in the 2010s. In the version that actually happened, the reconnaissance mission became the final mission, the snapshot became the full archive, and the planet has been running at 1,500 kilometers per hour through the entirety of the intervening silence. When Voyager's images of Neptune arrived at JPL in August 1989, the scientists looking at the great dark spot reached for the comparison that seemed most available: Jupiter. Jupiter's great red spot is the most famous persistent storm in the solar system. It has been continuously documented since 1830. Observations from the 1600s may represent the same storm, currently about 1.3 times the diameter of Earth, somewhat smaller than its historical extent but unchanged in fundamental character. It persists through centuries of continuous telescopic observation without any sign of permanent dissolution. Amateur astronomers with modest instruments can see it from their backyards on clear nights. It has been there for every human lifetime anyone now living can remember. It is, in every practical sense, a permanent feature of Jupiter. The Great Dark Spot was a high-pressure anticyclone rotating counterclockwise in Neptune's southern hemisphere, generating bright cloud structures along its southern boundary, clearly organised, clearly active. It was larger than Earth. It looked like the template. The assumption of permanence was not careless. It followed from the most directly applicable analogy available. Large storm, similar physics, similar scale, similar visual organisation. Scientists assumed it would be there when any future mission arrived. In 1994, the Hubble Space Telescope pointed its instruments at Neptune. The storm was gone. Not smaller, not fading. Gone. The Great Dark Spot that Voyager had photographed across 13,000 kilometres of Neptune's southern hemisphere in August 1989 was simply absent. A storm the size of Earth appeared, then vanished, and nobody saw it leave. The absence was not ambiguous. Hubble had the resolution to detect a feature of that size easily. Where the Great Dark Spot had been, there was undisturbed background atmospheric circulation. Whatever had organised into that storm had dissolved back into the atmosphere somewhere in the 5 years between 1989 and 1994, and no instrument had been watching when it happened. To understand why this is so different from what happens at Jupiter, you need to look at what Jupiter's atmosphere provides its storms beyond the energy to sustain them. Jupiter's atmosphere is organised. It has well-defined east-west bands, alternating zones and belts that have maintained their general structure since Galileo first observed Jupiter in 1610. The light zones and dark belts flow in alternating directions, creating long-lived jet streams at the boundaries between them. These bands are not temporary features. They have been mapped and tracked by every telescope capable of resolving Jupiter's disk for 400 years. The Great Red Spot sits embedded between two of these stable bands. The jet streams on its northern and southern boundaries constrain its latitude, prevent it from drifting, and shield it from the shear forces that would otherwise erode its organised structure. The storm and its environment have reached an equilibrium that allows the pressure system to persist indefinitely. Neptune's atmosphere cannot provide this stability. The extreme wind speeds that make Neptune the most chaotic planet in the solar system also prevent the atmosphere from settling into organised, long-lived banding. Neptune's jet streams are not stable, laminar flows that define atmospheric bands. They are extreme, variable, high-energy currents that continuously erode and reshape whatever forms within them. A large anticyclone that forms on Neptune forms inside an environment that is actively hostile to its persistence. The same energy that creates the storm eventually destroys it. You think Neptune has storms like Jupiter. It does, in the sense that anticyclones form, but they do not last. You think a storm the size of Earth is too large to simply dissolve. It is not. You think the disappearance of the Great Dark Spot was unusual. It was not. This is the pattern. Since Hubble confirmed the Great Dark Spot's absence in 1994, systematic monitoring has documented the Neptunian storm life cycle in partial detail. New dark spots have appeared and dissolved. A large dark spot appeared in Neptune's northern hemisphere in 2018, the first confirmed in Neptune's northern hemisphere, demonstrating the phenomenon occurs across both hemispheres. In 2020 and 2021, Hubble tracked a dark spot approaching Neptune's equatorial region. Atmospheric models predicted it would dissipate as it entered the equatorial zone, where jet stream structure changes in ways thought to destabilize organized storm systems. Instead, the spot shed a smaller dark fragment that separated and drifted independently. The main spot survived. The models were wrong. Each new observation of Neptune's atmosphere reveals something the existing models did not anticipate. Each anomaly requires revision. Each revision reveals another gap. 35 years after Voyager's 4-hour visit, the basic physics of how Neptunian storms form, how they evolve, and what determines when they dissolve has not been described in a complete theoretical model confirmed by observation. The pattern is not just that storms disappear. It is that the atmosphere is too energetic to allow anything to persist. Jupiter has a weather system powerful enough to maintain a storm for centuries. Neptune has a weather system so powerful that it cannot maintain a storm even for a decade. The two planets are both driven by internal heat, but Neptune's internal heat is proportionally larger and distributed in a way that continuously disrupts any organized structure before it can stabilize. The atmosphere is always in the process of both building and erasing simultaneously at every scale. Here is what the 4-hour visit means in this specific context. Voyager photographed the Great Dark Spot at what appeared to be a mature organized stage. It looked permanent. Scientists assumed any follow-up mission would find it waiting, and by the time any instrument looked closely at Neptune again, the storm was gone, and we missed the entire process of its dissolution. We have a before photograph from 1989. We have a confirmed absence from 1994. We have nothing in between. An event that produced and then erased a weather system larger than Earth occurred in a 5-year window when no human instrument was positioned to watch it. Whatever the Great Dark Spot looked like as it came apart, whatever dynamics finally overwhelmed its organized structure, that record does not exist. The atmosphere that erased it has continued running at 1,500 kilometres per hour, building new storms and dissolving them in a cycle that has been running since before any human ever looked up at the night sky. The comparison with Jupiter's persistence illustrates something deeper about the relationship between energy input and atmospheric organization. Jupiter's internal heat output is large in absolute terms, but it is distributed relatively evenly and does not overwhelm the tendency of the Jovian atmosphere to organize into stable zonal bands. Jupiter's atmosphere has found an equilibrium, a pattern of east-west circulation that has changed only gradually over centuries for the entire period of human observation. The Great Red Spot is not fighting the atmosphere. It is part of an organized system that holds it in place. Neptune's internal heat output is proportionally larger relative to the planet's size, and it is distributed in a way that continuously injects energy into the atmospheric circulation faster than organized structure can establish itself. The deep convection driven by that heat mixes the atmosphere on timescales shorter than those needed for stable zonal banding to develop. Any organized structure that forms does so in an environment of continuous disruption. The jet streams that created it are also eroding it. The temperature differences that drive it are being mixed away by the same convection that created them. The balance point where a large storm can anchor itself and persist does not exist at Neptune the way it exists at Jupiter. This is not merely a quantitative difference between two weather systems. It is a qualitative difference between two types of planetary atmosphere. Jupiter has found a stable state. Neptune has not, and may not be able to. The energy input is too high, the mixing too thorough, the system too far from equilibrium for any large structure to settle into a persistent configuration. Neptune is a planet whose atmosphere is always in the process of both building and destroying simultaneously at every scale. The storms are the visible surface of Neptune's strangeness. What lies beneath the cloud tops, in the invisible architecture of the planet itself, is stranger still. The Hubble monitoring data collected since 1994 has produced a partial picture of the Neptunian storm life cycle that is more complex than the single Voyager snapshot suggested. The Great Dark Spot was not an anomaly. It was an instance of a recurring process. Neptune regularly generates dark anticyclonic storms at various latitudes, and those storms regularly dissolve. The life cycle, from formation to dissolution, appears to span somewhere between 1 and several years, in the cases observed long enough to track completely. What triggers formation is not well characterized. The atmospheric conditions that allow a large anticyclone to organize are presumably related to local wind shear and temperature structure, but the specific trigger at a particular location and time is not captured by any validated model. The Hubble data suggests dark spots form somewhat randomly in latitude and timing, rather than at predictable locations or intervals. The atmosphere does not follow a regular cycle producing storms at known times. It produces them according to some internal dynamic that we cannot yet predict or model from Earth. What triggers dissolution is similarly unclear. The 2020 and 2021 observations of a dark spot surviving an equatorial transit that models predicted would destroy it demonstrated that the dissolution process is not governed simply by the large-scale atmospheric structure. The spot shed a fragment and continued. Whatever determines when a Neptunian storm finally dissolves is not captured by models built from knowledge of other planetary atmospheres. There is an uncomfortable implication. The single Voyager visit caught Neptune at a particular moment, with the Great Dark Spot in a particular state. We have no way to know whether that moment was representative of Neptune's typical atmospheric state. The atmosphere might look substantially different at other points in Neptune's 165-year orbital cycle. Seasonal changes on a planet with a 165-year orbital period occur on timescales that dwarf any human scientific program. The 4 hours Voyager spent at Neptune might have caught an unusually active moment, an unusually quiet one, a particular seasonal phase, or something with no particular pattern to it. Without sustained observation across a substantial fraction of that cycle, we cannot determine which. This is not an academic concern. It affects how we interpret the 1/500 km/h wind speed. We know Neptune's wind was moving at that speed in August 1989. We do not know whether it is always at that speed, or whether it varies significantly with season. We do not know whether the Great Dark Spot was forming, mature, or declining when Voyager photographed it. We know it was gone 5 years later. The single visit, combined with the planet's extremely long orbital period, means our entire picture of Neptune's dynamics is a snapshot of unknown representativeness. The atmosphere is still running. The storms are still forming and dissolving. We are watching from a distance with instruments that cannot see below the cloud tops, measuring a planet that showed us enough in 4 hours to know that the things we cannot yet see are probably as surprising as the things we have seen. The storms are the visible surface of Neptune's strangeness. What lies beneath the cloud tops, in the invisible architecture of the planet itself, is stranger still. The storm was larger than Earth, and it vanished between visits. That single fact contains the entire character of Neptune, a planet energetic enough to build structures at planetary scale, a planet chaotic enough to erase those same structures before any instrument can return to study them, something too large to ignore and too brief to track. The most chaotic planet in the solar system earned that name not from any single measurement, but from the combination. The wind that should not exist, the storm that could not persist, the atmosphere that builds and destroys on scales that dwarf anything else in the solar system. The storm is gone. The atmosphere that made it and destroyed it is still running. The magnetic field is the invisible architecture of a planet. You use it every time you navigate with a compass. Migrating birds use it to cross continents. The northern lights exist because of it. The field extends tens of thousands of kilometres into space, shaping how charged particles move through the region around Earth and deflecting the constant outflow of energetic particles from the Sun. Earth's field is generated by its core. The planet has a solid inner core and a liquid outer core, both primarily iron and nickel. Heat flowing outward from the inner core drives convection in the liquid outer core. The planet's rotation, via the Coriolis effect, shapes that convection into organized patterns. Conducting liquid metal in organized circulation generates electric currents. Electric currents generate magnetic fields. The field extends from the deep interior into space around the planet, creating the magnetosphere, the region dominated by Earth's magnetic influence. That field is not decorative. It stands between Earth's atmosphere and the solar wind, a constant stream of charged particles from the Sun at several hundred kilometres per second. Without the field deflecting it, the solar wind would gradually erode the upper atmosphere over millions of years. Mars provides the confirmation. Early in its history, Mars likely had a core dynamo similar to Earth's. When the Martian core cooled and solidified, ending the convective circulation, the field collapsed. Without magnetic protection, the solar wind began stripping the Martian atmosphere. Over billions of years it thinned from something that may once have supported liquid water to the present atmosphere, 1% of Earth's atmospheric pressure. The loss of the magnetic field and the thinning of the atmosphere are causally connected. Earth's field is also nearly aligned with its rotation axis. The magnetic North Pole sits in the Canadian Arctic, a few hundred kilometres from the geographic North Pole. This offset is small enough that compass navigation has been accurate for centuries. The alignment follows from how the core dynamo generates the field. Liquid core circulation shaped by planetary rotation produces a dynamo whose field axis tends to align with the rotation axis driving it. The generator and the field it generates share geometry with the thing that powers them. Now look at Neptune. Neptune's magnetic field is tilted 47 degrees from its rotation axis. 47 degrees. On Earth, a tilt of that magnitude would place the magnetic North Pole somewhere near Tunisia, over the Mediterranean Sea. Compass needles everywhere on Earth would point toward the wrong ocean, on the wrong side of the planet. A navigator in London would aim toward the Indian Ocean. A navigator in Tokyo would aim toward Europe. Every map produced using magnetic north as a reference would carry an error so large that the correction required to find true north would exceed the navigational precision of any instrument using magnetic reference alone. Neptune's magnetic field is so misaligned it would make every compass on Earth useless. But the axis tilt is not the deepest part of Neptune's magnetic anomaly. Earth's field, despite its slight tilt, is centered on the planet. The core dynamo sits in the deep interior, and the field it generates emerges from approximately the planetary center. The field is roughly dipolar, like a bar magnet positioned near the center of Earth, with field lines arcing from one magnetic pole to the other in a pattern that, while not perfectly symmetric, has approximate symmetry about the magnetic axis. Neptune's magnetic dipole is offset from the planet's geometric center by approximately 13,500 kilometers. Neptune's radius is roughly 24,622 kilometers. The source of Neptune's magnetic field is displaced more than half a planetary radius from the center. What this produces is not a slightly imperfect dipole, it is a dramatically asymmetric field. The northern and southern hemispheres experience qualitatively different magnetic environments, not mirror images at opposite polarity, but environments with different intensities, different geometrical structures, different relationships to incoming solar wind particles. As Neptune rotates, the off-center, off-axis dipole sweeps through space in a complex tumbling motion. The magnetosphere shifts its orientation relative to the solar wind over the course of each 16-hour Neptunian day. A spacecraft in orbit around Neptune would encounter a dramatically different magnetic environment at different points in each orbit, not because it had moved into a different region of space, but because the magnetosphere itself had rotated under it. The field is tilted 47 degrees, making prediction by navigation-style reference impossible. It is offset 13,500 kilometres from the centre, making dipole approximations fail. It tumbles on a 16-hour cycle, making any static model of the magnetosphere wrong within hours. Each characteristic is independent. Each makes the field harder to model. Together they produce a magnetic environment unlike anything we have encountered at any well-studied planet. Auroras at Neptune cannot be predicted to occur near any particular latitude. On Earth, auroras form in oval bands around the magnetic poles because the magnetic axis is close to the rotation axis. Neptune's magnetic poles are not near its geographic poles. Depending on where the field lines emerge at any given moment in the rotation cycle, auroral activity can occur almost anywhere on the planet. Voyager detected aurora-like emissions at Neptune across a wide range of latitudes. 4 hours was not enough time to characterize the pattern. The anomaly is not unique to Neptune. Uranus has a magnetic field tilted 59 degrees from its rotation axis and similarly offset from its geometric centre. Both ice giants, measured independently by separate Voyager flybys in 1986 and 1989, show the same pattern of anomalous magnetic field geometry. Gas giants, Jupiter and Saturn, have fields much more closely aligned with their rotation axes, consistent with the standard core dynamo model. Rocky planets, Earth, Mars, Mercury, also broadly consistent with interior dynamo models. What is it about ice giants specifically that produces this? The theoretical answer involves composition. Jupiter and Saturn are primarily hydrogen and helium. Under extreme pressures deep in their interiors, hydrogen transitions to a metallic state in which it conducts electricity freely. This metallic hydrogen layer sits deep in the planet close to the centre, and its circulation in the rotating planet generates the magnetic field close to the core. The result is a field approximately centred and approximately aligned with the rotation axis. Neptune and Uranus contain large proportions of water, ammonia and methane under extreme pressure. These materials, called ices in planetary science, may exist in a phase called superionic matter at the temperatures and pressures inside ice giant interiors. In superionic water, oxygen atoms form a crystal lattice, while hydrogen atoms move freely through it as conducting ions. This material conducts electricity, but the conducting region may not be at the planetary centre. It may be a conducting shell at a certain depth within the planet, above the denser interior. A shell dynamo generates a magnetic field with fundamentally different geometric properties than a core dynamo. The field produced by a conducting shell would be offset from the planetary centre and tilted at a large angle from the rotation axis. The result would look exactly like what Voyager measured at Neptune: off-axis, off-centre, asymmetric, tumbling. The shell dynamo model is consistent with all available external measurements. It has not been confirmed. No instrument has ever been inside Neptune. The evidence consists of the external field geometry measured by Voyager in 4 hours, laboratory high-pressure experiments on water and ammonia, and theoretical models of interior structure inferred from the planet's bulk properties and gravity field. The model is the best current inference from incomplete evidence gathered in a single brief transit 35 years ago. Understanding Neptune's magnetic field matters beyond Neptune. Ice giants appear to be the most common planetary type in the galaxy based on exoplanet surveys. Every model we apply to characterize ice giant planets orbiting other stars is built on data from Neptune and Uranus. The Neptune data is a single 4-hour transit. The Uranus data is similar. Our understanding of how the most common planetary type generates its magnetic field rests on 8 combined hours of close-range observation. The field tells you about the deep interior. The interior is where the heat comes from that drives the wind. The wind is what erases the storms, all of it connected, all of it resting on 4 hours of data, all of it still only partially explained. There is one more dimension that is not in the atmosphere, not in the magnetic field, but in the orbit of a moon that has no business being there. The shell dynamo model makes specific predictions that could be tested by a dedicated mission. If a conducting shell is responsible for Neptune's field, the field should have a specific radial structure, with the dipole component generated at a characteristic depth below the cloud tops. That depth should correlate with the pressure and temperature conditions at which supersonic water forms based on laboratory experiments. The ratio of the dipole component to higher-order components of the field should follow specific patterns distinguishing shell dynamos from core dynamos. All of these predictions are checkable, in principle, by a spacecraft with modern magnetometry instruments, making thousands of orbital passes. None of them are checkable with the data currently available. The laboratory experiments attempting to replicate conditions in Neptune's interior are genuinely challenging. Creating pressures of millions of atmospheres and temperatures of thousands of degrees in a controlled setting requires large specialized facilities and produces those conditions for fractions of a second. The measurements possible under such extreme conditions are limited. Whether water becomes supersonic at the specific pressure and temperature conditions found at the characteristic depth in Neptune's interior, rather than at slightly different conditions that would shift the depth of the conducting shell, is constrained but not definitively resolved by available experiments. The magnetosphere that results from Neptune's anomalous field creates a dynamic environment unlike anything we have well characterized at other planets. On a timescale of 16 hours, one Neptunian day, the magnetosphere shifts its orientation relative to the solar wind by tens of degrees. Radiation belts inside the magnetosphere, regions of trapped energetic particles shaped by the field geometry, shift with each rotation. A spacecraft trying to plan observations or thermal management around the radiation environment would need detailed maps of how the field and the belts change through the full rotation cycle. Voyager's single transit measured the field at one phase of this cycle. The other phases have never been directly sampled. This matters for any future mission. Engineering a spacecraft to operate safely in Neptune's magnetosphere over years requires understanding the radiation environment across all phases of the 16-hour cycle and across multiple seasons. The data needed to specify that environment does not exist. The Voyager transit is one data point in a cycle that has been repeating, unmeasured, for 35 years since the spacecraft departed. What the magnetic field tells you, beyond its own strangeness, is that Neptune's interior is structured in ways we have not directly observed, operating on physical principles that are still being worked out from the outside. The wind tells you about the atmosphere. The magnetic field tells you about the deep interior. Both point at the same condition, a planet visited once, in 4 hours, whose fundamental physics at every level is still only partially described. The daily variation of Neptune's magnetosphere, the tumbling of the off-center dipole through space over each 16-hour rotation, creates a phenomenon that has no close parallel at any planet we understand well. At Earth, the magnetosphere is approximately static in shape. It is compressed on the sunward side by the solar wind and stretched into a long tail on the far side. but the basic geometry persists from day to day. Magnetic storms caused by particularly intense solar wind events can alter the magnetosphere temporarily, but the underlying shape is stable. Planning operations in Earth's near-space environment is in this sense predictable. At Neptune, the magnetosphere is never in the same configuration. A spacecraft at a fixed orbital position relative to Neptune would find itself inside a dramatically different magnetic field environment at different points in the 16-hour cycle. The radiation exposure from energetic particles trapped in the field would vary substantially. The interaction between the magnetosphere and any radio signals transmitted through it would change. The ability to point an instrument at a specific surface feature of Neptune would be complicated by the fact that the particle environment surrounding the instrument was constantly changing in ways that depend on the phase of the rotation cycle. None of this means a mission to Neptune is impossible. It means that designing one requires detailed knowledge of the time-varying magnetic field structure that Voyager's single transit cannot provide. The engineering uncertainty for a Neptune mission is larger than for missions to Saturn or Jupiter, partly because the radiation environment is less well characterized, and characterizing it from Earth orbit is not possible with the required precision. This is one of the reasons the planetary science community argues that a first step at Neptune should be an orbiter, not just because an orbiter produces more science than a flyby, but because the magnetic field mapping that an orbiter would conduct in its first year of operation would dramatically reduce the engineering uncertainty for any future mission. The 4-hour Voyager transit provided enough information to demonstrate the anomaly. An orbiter would provide enough information to understand and work within it. What the magnetic field tells you, beyond its own strangeness, is that Neptune's interior is structured in ways we have not directly observed, operating on physical principles still being worked out from the outside. The wind tells you about the atmosphere. The magnetic field tells you about the deep interior. Both point at the same condition: a planet visited once, in 4 hours, whose fundamental physics at every level is still only partially described. Consider what it would take to characterize Earth's magnetic field to the level of detail we use in everyday navigation, using only a single hour of measurements from a passing spacecraft. The answer is that you could not. You would know the approximate field direction, the approximate field strength at the point of closest approach, the rough tilt of the dipole from the rotation axis. You would not know the daily variation, the seasonal variation, the response to solar wind events, the three-dimensional structure of the radiation belts, or any of the other details that make Earth's magnetosphere useful to model and understand. That is the state of our knowledge of Neptune's magnetic field, a passing snapshot that reveals the anomaly but does not begin to characterize it. The anomaly has a name, a scale, and a theoretical explanation. It does not yet have a confirmed description. That is the state of Neptune's magnetic field, known to be profoundly different from what a simple planetary dynamo model would predict, partially explained by a theoretical framework that has not been confirmed, measured once in 4 hours by a spacecraft that is now in interstellar space. The deep interior that generates the field has never been sampled. The daily variation of the field that shapes the near-Neptune environment has never been mapped. The connection between the field and the atmospheric dynamics has never been traced in detail. There is one data point. There should be thousands. Here is a rule embedded so deeply in how the solar system works that most people have never had occasion to notice it. Moons orbit in the same direction their planet rotates, not as a tendency with exceptions, as a mechanical consequence of formation. Planets form from rotating disks of gas and dust surrounding young stars. The disk has a net rotational direction, inherited from the molecular cloud that collapsed to produce the star. The planet forms within this rotating disk and inherits its direction. Moons that form from the disk material around the planet orbit in the same direction because they formed from the same rotating source. Angular momentum is conserved. Everything moves the same way because everything came from the same rotating origin. Earth's moon orbits prograde. Jupiter's 4 Galilean moons, each large enough to be classified as a planet if they orbited the Sun, all orbit prograde. Saturn's large moons orbit prograde. Uranus has a collection of mid-sized moons, all prograde, despite Uranus's extreme 98-degree axial tilt. The rule is reliable enough that when planetary scientists encounter a large moon in retrograde orbit, they treat it not as an anomaly but as evidence. Large exceptions to formation rules require large explanations. Neptune's largest moon, Triton, orbits backwards. Not at a slight inclination attributable to some modest early perturbation. A full retrograde orbit, moving in the direction opposite to Neptune's rotation, in a path tilted about 23 degrees from Neptune's equatorial plane. The only large moon in the solar system confirmed to orbit retrograde, and the retrograde character of its orbit was not something that developed gradually. Triton arrived at Neptune already moving in the wrong direction. Neptune's gravity caught it. Triton orbits backwards, and that single fact tells us Neptune's history was violent. A large moon cannot form in retrograde orbit. Material in the disk surrounding a forming planet moves prograde, and moons form from that material by accretion, inheriting its direction. For a large moon to orbit retrograde, it had to arrive from outside the system. Capture is the only mechanism that produces this configuration. Gravitational capture of a large body is not simple. When an object falls toward a planet, it gains kinetic energy from the gravitational field. When it swings past and departs, it loses that energy again. A simple two-body encounter is reversible. The trajectory is bent, but the object escapes with the same speed it arrived with. For permanent capture, energy must be removed from the incoming object during the encounter, leaving it with insufficient kinetic energy to escape. The leading mechanism proposed for Triton's capture is a binary exchange interaction. Before reaching Neptune, Triton may not have been a single object. It may have been part of a gravitationally bound pair, two icy bodies orbiting each other as they move together through the outer solar system. When this binary pair made a close approach to Neptune, the planet's tidal forces disrupted the binary's internal orbit. The energy released by the separation was transferred in a way that left one object, Triton, in a bound orbit around Neptune while ejecting the other on a hyperbolic trajectory away from the planet. The escaped object carried the excess energy. Triton was left bound. Binary exchange capture requires specific geometry, specific approach speed, and specific binary configuration at the moment of closest approach. The probability for any single encounter is low. The outer solar system contains many binary objects, and 4.5 billion years provide sufficient time for rare events to accumulate. The statistics eventually produced the encounter. Before the capture, Triton was almost certainly a Kuiper Belt object, a large icy body from the outer solar system in the same category as Pluto. Its composition of nitrogen ice, methane ice, water ice, and rock is consistent with Kuiper Belt origin. Pluto and Triton are siblings in origin, both large icy bodies formed in the same region of the outer solar system. Pluto still orbits the Sun independently. Triton was pulled from that origin into captivity around Neptune. What happened next was not quiet. Neptune almost certainly had a family of regular prograde moons before Triton arrived, formed in the standard way from the disk surrounding the young planet. When Triton entered the system in its retrograde orbit, initially in a highly elongated path crossing the orbital regions of those original moons, the disruption was severe. Each passage brought potential collisions and close gravitational encounters. Stable orbits were perturbed. Bodies in crossing orbits collided and generated debris. Over hundreds of millions of years, through cascading collisions and ejections, Neptune's original prograde moon family was effectively eliminated. Some members were thrown inward to destruction by Neptune's tidal forces. Others were flung outward and escaped the system. The collisions produced debris that subsequent interactions further dispersed. Triton arrives. Original moon's orbits become unstable. Collisions begin. Collisions generate debris. Debris creates further perturbations. Survivors are ejected by close encounters with Triton. Each consequence makes the next consequence more likely. The original system does not simply lose members, it is comprehensively destroyed. Triton has already destroyed one family of moons. Neptune's original system is gone. The 16 small moons currently known around Neptune beyond Triton are thought to be debris from this destruction, or small objects captured afterward. Triton accounts for more than 99.5% of the total mass orbiting Neptune. The remaining 16 moons combined are less than half of 1%. They are rubble, fragments, the remnants of a system that no longer exists. Triton itself, observed in close detail for the only time by Voyager in 1989, is one of the stranger surfaces in the solar system. It is approximately 2,707 kilometres in diameter, the 7th largest moon in the solar system. Its surface temperature is about minus 235 degrees Celsius. At that temperature, nitrogen, which makes up 78% of Earth's atmosphere, is not merely frozen. It is rock-solid ice on Triton's surface. Carbon monoxide, a gas at room temperature, froze solid billions of years ago. Methane, the gas in a kitchen stove, is a pale, crystalline mineral on Triton's surface. Water behaves not like the ice in a freezer, but like granite. Harder, denser, utterly inert under any force a biological organism could apply. Nothing built by human engineering is designed to survive in an environment this cold. Material science has no routine vocabulary for what happens to matter at minus 235 degrees because nothing in any industrial context operates there. And yet Triton is geologically active. Voyager photographed dark streaks across Triton's south polar region, geyser deposits. The geysers are powered by sunlight. Sunlight at Neptune's distance, 1/900th of what reaches Earth, can still penetrate Triton's transparent surface nitrogen ice and be absorbed by the darker material beneath. That absorbed energy heats the dark substrate, enough to vaporize the nitrogen above it. The expanding gas escapes upward through the ice as a jet, carrying dark particles to heights of about 8 kilometres. Triton's thin nitrogen atmosphere catches the ejected material and deposits it in dark streaks aligned with the prevailing wind. A geyser powered by a fraction of 1% of Earth's sunlight, erupting on a surface colder than any environment humans have ever worked in. Triton also has a thin nitrogen atmosphere, detectable as a faint haze at the moon's limb in Voyager's images. Too thin for weather, too thin for meaningful insulation, but present, making Triton one of only a few moons in the solar system known to have any atmosphere at all. The most consequential fact about Triton is what it is doing right now. Triton is falling toward Neptune. Its retrograde orbit is gravitationally unstable on geological timescales. For prograde moons, tidal interactions with the rotating planet add energy to the orbit over time, pushing the moon slowly outward. Earth's moon recedes from Earth at 3.8 centimetres per year. For Triton, with its retrograde orbit, the tidal interaction is reversed. The tidal bulge Triton raises on Neptune is dragged in the wrong direction by the planet's rotation. Tidal forces remove energy from Triton's orbit rather than adding it. Triton is spiralling inward. in approximately 3.6 billion years, Triton will cross the Roche limit, the distance from Neptune at which tidal forces exceed the self-gravity holding the Moon together. At that point, Neptune will begin tearing Triton apart. The outer layers will separate, the Moon will fragment, the material will spread around Neptune's orbital path and form a ring system. Neptune's current, faint, narrow rings will become a massive band of debris assembled from the destruction of its largest moon. In a few billion years, Neptune will look more like Saturn looks today, defined by its rings, those rings built from a moon whose arrival destroyed the system that preceded it. Neptune is slowly pulling its largest companion toward an end it cannot survive. The pattern holds from the planet's earliest history to its distant future. A violent capture event eliminated the original moon family. The captured moon is now falling. The ring system that results will be built from the wreckage of the survivor of the first destruction. The violence did not end when Triton arrived. It shifted timescale. Neptune has already destroyed one family of moons and is slowly pulling another to its death. There is a question about Triton that Voyager could not answer, and that has become more pressing as the outer solar system has revealed more subsurface oceans at unexpected locations. Does Triton have a subsurface ocean? Before Cassini's discovery of Enceladus' liquid water ocean in 2005, the idea of subsurface oceans beneath the icy shells of outer solar system moons was considered theoretically possible, but poorly constrained by observation. Since then, the evidence for subsurface oceans at Europa, Ganymede, Callisto, Enceladus and Pluto has changed the picture. Liquid water environments in the outer solar system appear substantially more common than the classic picture of frozen worlds beyond the snowline had suggested. The conditions that maintain liquid water, tidal heating, radiogenic decay in rocky cores, chemical antifreeze from dissolved ammonia and salts, can operate at distances from the Sun where surface temperatures are hundreds of degrees below the freezing point of pure water. Triton sits in an interesting position with respect to this question. Its retrograde orbit means it is subject to tidal forces from Neptune that operate differently from the tidal forces on a prograde moon. During the long period when Triton's originally highly eccentric captured orbit was being circularized by tidal forces, Triton would have experienced substantial tidal heating. The current nearly circular orbit represents a lower heating configuration than the historical orbit that led to it. Whether the historical heating was sufficient to establish a liquid water layer in the interior, and whether current tidal heating is sufficient to prevent it from refreezing, depends on Triton's internal composition and structure, which Voyager could not determine. The surface characteristics Voyager observed are consistent with geological resurfacing, internal processes that have modified the original surface. The presence of geysers, the thin nitrogen atmosphere, and the unusual terrain features called cantaloupe terrain, a surface covered in circular depressions resembling the skin of a melon, all suggest a world that has not been simply frozen and inert since its formation. Whether liquid water is currently involved in Triton's geology, or whether a liquid layer persisted until recently, or whether the geological activity is driven entirely by other mechanisms, cannot be determined from the images Voyager was able to take in its brief flyby. If Triton has a subsurface ocean, it would be the farthest confirmed liquid water environment from the Sun in the solar system, more than 30 times farther from the Sun than Earth, on a captured Kuiper Belt object in retrograde orbit around an ice giant. The implications for the distribution of potentially habitable environments in the solar system would be substantial. The conditions that maintain liquid water at Triton, if they exist, would expand the known range of conditions under which liquid water environments can occur and persist. The ring system that will form from Triton's eventual destruction will not be a simple debris field. The process will unfold over millions of years following the moment Triton crosses the Roche limit. As the Moon begins to fragment, The largest pieces will move into new orbits around Neptune before they themselves are further broken by tidal forces and collisions. Over time, the size distribution of the debris will shift towards smaller particles. The material will spread to fill a ring around Neptune's orbit. The specific structure of the resulting ring will depend on the composition and internal structure of Triton, which we have not directly measured. Whether it will resemble Saturn's icy rings or something more like the dark, narrow rings of Uranus is not predictable from what we know. What is predictable is that it will happen on a timescale longer than the current age of Earth, driven by the same tidal mechanics that are already operating on Triton with every orbit it completes around Neptune today. The Pluto-Triton comparison is worth dwelling on, because it is one of the stranger symmetries in the solar system's history. Both Pluto and Triton formed in the outer solar system, probably in the Kuiper Belt region beyond Neptune's current orbit. Both are large icy bodies of similar size and similar composition. Pluto is roughly 2,377 kilometres in diameter. Triton is roughly 2,707 kilometres. Both have nitrogen-dominated surfaces and atmospheres. Both show evidence of geological activity driven partly by the faint sunlight reaching the outer solar system. Both have rocky interiors surrounded by icy shells. The difference between them is the encounter with Neptune. Pluto kept its independence. It retained a binary companion, Charon, which orbits Pluto in a system that has evolved stably for billions of years. Pluto orbits the Sun in a 248-year resonance with Neptune that keeps the two worlds from ever coming dangerously close. Pluto has had time to settle into whatever equilibrium its current state represents. Triton lost its independence. Pulled from the Kuiper Belt by a chance encounter with Neptune billions of years ago, it has been in a retrograde orbit ever since, systematically destroying what it found when it arrived and now being slowly destroyed itself. The two worlds started in the same region, formed in the same era of similar material. One orbits the Sun in a stable resonance, the other is falling toward Neptune. When the New Horizons spacecraft flew past Pluto in 2015, the images it returned showed a world of extraordinary complexity. Vast nitrogen glaciers, towering mountains of water ice, a surprisingly young surface in some regions suggesting ongoing geological activity. If Triton, of similar composition and similar size, has a comparable level of internal activity, the surface Voyager photographed in 1989 may represent only a fraction of Triton's true character. The cantaloupe terrain, the geysers, the thin atmosphere may be hints at a more complex world than the 4-hour visit could reveal. Whether Triton is more like Pluto than we have been able to determine from the available data is a question that requires proximity and time to answer. Proximity and time are exactly what Neptune has never received. The orbital mechanics of Triton's fate operate on timescales that dwarf human history so completely that the numbers lose their texture. 3.6 billion years is not merely a long time, it is longer than the current age of Earth. It is longer than the time from the formation of the first oxygen-producing life on Earth to today. It is so far in the future that the Sun will have changed substantially before Triton crosses the Roche limit, and yet the process driving that future destruction is happening now, with each orbit Triton completes. The inspiral is not a future event, it is a present fact. Triton is closer to Neptune today than it was 100 years ago. It will be closer still in another 100 years. The planet is pulling at it continuously by a force that is real and measurable on a timescale that only appears abstract because of the gap between human lifetimes and orbital mechanics. The 17 moons of Neptune, Triton plus the 16 small inner moons, represent a system that has been reconfigured at least once in its history and will be reconfigured again. The small inner moons orbit in a region that Triton's inspiral will progressively disturb. As Triton moves inward over the next billion years, the gravitational perturbations it imposes on the small moon orbits will intensify. Some of those small moons may be destabilized and eventually fall into Neptune. Others may be perturbed into crossing orbits with each other, producing new collisions and debris. The ring system that will eventually form from Triton's destruction will incorporate material from Triton and from whatever becomes of the small inner moons in the time between now and then. Neptune is not done being violent, it simply operates on timescales that feel like permanence from the outside. Stack what Voyager's 4 hours revealed. Wind speeds of 1,500 kilometres per hour on a planet receiving 1/900th of Earth's solar input. Powered by formation heat, 4.5 billion years old. A storm the size of Earth that appeared and dissolved between visits, with no instrument watching either event. A magnetic field tilted 47 degrees off axis, generated from a location more than half a planetary radius from the planet's centre, following a theoretical model not confirmed by direct measurement. A large retrograde moon that arrived through a violent binary exchange capture destroyed the original moon system and is now on a multi-billion-year inward path toward a collision that will produce a ring system from its own wreckage. All of that from 4 hours of data gathered in August 1989 by instruments designed in the 1970s aboard a spacecraft that launched when Elvis Presley was still alive. We have visited Neptune once for 4 hours 35 years ago. Hold that against the record at other targets. Mars has received more than 50 missions since the 1960s. Active rovers are currently driving across its surface, drilling into rocks, analysing chemical composition of soil samples. We have flown a helicopter in the Martian atmosphere. We have placed seismometers on the surface to measure Mars quakes. We are preparing to return samples from the Martian surface to Earth for laboratory analysis. The Martian surface is, in some places, better documented than the floor of Earth's deep oceans. Saturn. Cassini orbited it from 2004 to 2017, 13 years of continuous observation. 293 complete orbits, 127 close flybys of Saturn's moons, more than 450,000 images. Cassini discovered that Enceladus has active geysers of liquid water erupting from a confirmed subsurface ocean, transforming the search for habitable environments in the outer solar system. It watched storms form and evolve across full seasonal cycles. The pre-Cassini and post-Cassini understanding of Saturn are not more and less detailed versions of the same picture. They are qualitatively different pictures of a system whose true character was not apparent until sustained observation revealed it. Jupiter, currently being orbited by Juno since 2016, mapping the planet's gravity field and magnetic field at precision that revealed interior structures no prior model had correctly predicted. The Europa Clipper, launched in October 2024, is now en route to study the ocean beneath Europa's icy shell. Neptune, nothing, no orbiter, no atmospheric probe, no flyby in funded development. The 4 hours of Voyager data from August 1989 is the complete close-range dataset. It will remain the complete dataset for at least a full generation of planetary scientists. Cassini spent 4,145 days at Saturn. Voyager spent 4 hours at Neptune. Neptune's observational coverage is 0.02% of Saturn's. Every model of Neptune, every theoretical framework for the interior, atmosphere, magnetic field, and moon system is built from 0.002% of the observation time invested in a planet we now consider well understood. This is not invisible to the planetary science community. Ice giants are the least explored class of planet in our solar system. They are also the most common planetary type in the galaxy, based on exoplanet surveys. We may live in a galaxy where ice giants are the dominant planetary type, and our combined close-range observational dataset for the class is 8 hours. 2 flyby transits from the 1980s. A mission concept called Triton was developed specifically to begin closing this gap. Proposed to NASA in the late 2010s, Triton was a flyby mission targeting Neptune and Triton. It would have used a Jupiter gravity assist in the mid-2020s to reach Neptune in the early 2040s. Its goals included measuring Neptune's magnetic field in far more detail than Voyager's single transit allowed, imaging Triton's geyser activity at high resolution across multiple rotation cycles, and searching for evidence of a subsurface ocean at Triton. The case for a Triton subsurface ocean is not purely speculative. Enceladus, Saturn's small moon, has a confirmed liquid water ocean maintained by tidal heating. Triton, in its retrograde orbit around Neptune, is subject to tidal forces from Neptune that generate internal heat. Its surface chemistry, geyser activity, and atmospheric presence are consistent with the possibility of a liquid layer beneath the ice shell. If Triton has a subsurface ocean, it would be the most distant confirmed liquid water environment from the Sun in the solar system, with implications for how common liquid water environments are in the cold outer solar system. Trident was a finalist in NASA's New Frontiers program. It was not selected. The Dragonfly mission to Titan was chosen instead. Trident went back into the proposals file. The 2022 Planetary Science Decadal Survey identified an ice giant mission as a high scientific priority and recommended development of a flagship orbiter for Uranus as the highest priority large mission of the decade, noting Neptune as comparably important scientifically. The Uranus orbiter is in early development with uncertain funding and timeline. A Neptune mission has no equivalent programmatic standing. The James Webb Space Telescope has contributed a partial update. In 2022, Webb produced near-infrared images of Neptune's ring system at a clarity no prior observatory had achieved, revealing all 4 main rings and several faint structures simultaneously. These are genuine scientific contributions. Webb can image the rings from 1.5 million kilometres away. It cannot determine what those rings are made of, when they formed, or how fast they are changing. It can detect cloud features in Neptune's upper atmosphere. It cannot measure wind speeds below those clouds, probe the thermal structure at depth, or characterize the magnetic field. It can resolve Triton as a small disk. It cannot determine whether a subsurface ocean exists, measure geyser eruption rates, or characterize the thin atmosphere in the detail needed to understand its energy budget. The practical consequence of not returning to Neptune is not only a gap in scientific knowledge, it is a gap in capability. The instruments aboard Voyager 2 were state-of-the-art in the late 1970s, modern planetary science instruments, with 4 additional decades of development, would return data orders of magnitude richer. A modern magnetometer array making thousands of orbital passes would resolve Neptune's 3-dimensional field structure in enough detail to confirm or refute the shell dynamo model. A modern atmospheric probe descending through Neptune's atmosphere would measure wind speed profiles at depth, thermal structure below the cloud tops, and chemical composition at different pressure levels. None of this information exists. The only wind speed measurement we have for Neptune is the one Voyager made at the cloud tops in 1989. Neptune has an orbital period of 165 years. It completed its first documented full orbit in 2011, 165 years after its discovery in 1846. The single Voyager observation from 1989 represents 1 point in a 165-year cycle. Whether the winds measured in 1989 were typical, or represented a specific seasonal phase, or were anomalous in some way, cannot be determined without observations at other points in that cycle. A spacecraft staying at Neptune for several years would begin to address this. Whatever Neptune is doing that we have not yet noticed, because we have not had instruments near it for long enough to notice, remains unknown. Every hour Voyager spent at Neptune revealed something unexpected. We have had 4 of those hours. The planet has been running for 4.5 billion years. We have been to Neptune once for 4 hours 35 years ago. Everything we know about the most chaotic planet in the solar system came from that single window. The scientific case for returning to Neptune is not only about Neptune. It is about what Neptune and Uranus together can tell us about the class of planet that may be the most common in the galaxy. If ice giants are indeed the dominant planetary type in the Milky Way, then understanding how they generate their magnetic fields, how their atmospheres behave, and how their moon systems form and evolve is not merely an exercise in exploring our own solar system. It is preparation for understanding the most common context in which planets exist elsewhere. Every exoplanet survey we conduct, every spectrum of a distant planetary atmosphere taken with the James Webb Space Telescope or its successors, is filtered through models of what planetary atmospheres and planetary systems are doing. The models for ice giant planets are built primarily on data from Neptune and Uranus. The Neptune data is a 4-hour snapshot. The Uranus data is a similar flyby from 1986. The models we apply to thousands of ice giant exoplanets rest on 8 combined hours of close-range observation. That is not a comfortable state of affairs for planetary science. The community knows it. The 2022 Decadal survey acknowledged it when it identified ice giants as critically underexplored and designated a Uranus orbiter the highest scientific priority for the decade. The scientific argument for a mission is unambiguous. The political and budgetary argument is harder, involving competition among scientific priorities, the long lead times required for outer solar system missions, and the challenge of maintaining political support for a mission whose cruise phase to Neptune would take more than a decade. A Neptune orbiter launched in the early 2030s, using a Jupiter gravity assist, would arrive at Neptune in the early 2040s. It would orbit Neptune for several years, making continuous measurements of the magnetic field across thousands of complete planetary rotations, tracking atmospheric dynamics across seasonal changes, monitoring Triton's surface and geyser activity, and characterizing the ring system. The data would transform our understanding of ice giants in the way Cassini transformed our understanding of Saturn. Not incrementally, but qualitatively. The pre-mission and post-mission pictures would be as different from each other as the pre-Cassini and post-Cassini pictures of Saturn. That mission has not been funded. Neptune continues to run at 1,500 kilometres per hour, unobserved by any instrument near it, for the 35th consecutive year since Voyager departed. The silence is not the planet's. The planet is not silent. It is running at a speed that would erase any structure we could build, building and dissolving storms the size of Earth, tumbling its asymmetric magnetic field through space on a 16-hour cycle, slowly pulling Triton inward by an unmeasurable fraction of a millimetre with each orbit. The silence is ours. We looked once, 35 years ago, and we've been studying the echoes of that 4-hour conversation ever since. The data gap has a specific cost that extends beyond our understanding of Neptune. Every time an astronomer uses James Webb to take a spectrum of the atmosphere of an ice giant planet, orbiting another star, they interpret that spectrum using models of how ice giant atmospheres work. Those models are calibrated against data from Uranus and Neptune. The calibration data set for ice giants is 8 hours of flyby observations from the 1980s. The models work well enough to make the spectral interpretation plausible. They do not work well enough to make it definitive. When Webb detects what might be a temperature inversion in the upper atmosphere of a distant ice giant exoplanet, or what might be a signature of methane photochemistry, the interpretation depends on models built from instruments that could not see below the cloud tops of the only 2 local examples. The systematic uncertainties in those models are large precisely because the input data is so limited. A dedicated Neptune orbiter would not just improve our understanding of Neptune, it would dramatically improve the baseline for interpreting every ice giant exoplanet observation made by current and future telescopes. The scientific return would extend far beyond the Neptune system itself. The same point applies to understanding how ice giants affect their host stars' habitable zones and how they shape the architecture of planetary systems. In our own solar system, Neptune and Uranus shepherd the outer solar system, maintaining the Kuiper belt structure through gravitational resonances and acting as gravitational barriers that shape the delivery of comets and volatile material to the inner planets over billions of years. Understanding how ice giants behave dynamically, how they migrate over their host stars' lifetimes, how they interact with their moon systems and debris belts, requires the kind of detailed characterization that only sustained orbital observation can provide. Neptune is not just one more outer solar system target. It is the nearest example of the dominant planetary type in the galaxy. 4 hours of data from 1989 is what we have built our understanding of that dominant planetary type on. The gap between what we know and what we could know, if we returned with a mission designed to stay, is one of the larger outstanding gaps in planetary science. It will close eventually. The planet will be there, running at 1,500 kilometres per hour whenever that mission arrives. The question of when that mission arrives is not purely scientific. It is budgetary, political, and strategic. It involves prioritization among competing scientific goals, each of which has its own advocates and its own strong case. The decadal survey process that produced the current recommendation, Uranus first and Neptune closely behind, represents the best current collective judgment of the planetary science community about how to allocate limited resources across the range of outstanding scientific questions. That judgment placed Neptune high enough to name it explicitly as a priority, and not high enough to fund a mission in the current decade. What the science requires is a mission. What the budget has provided is a recommendation. The gap between those two things is where Neptune has been sitting for 35 years, since Voyager departed. The wind does not notice. The 4 hours of Voyager data have sustained 3 decades of active scientific work. Papers continue to be published using Voyager-Neptune data as primary input. Models of ice giant interiors, dynamo models of off-axis magnetic fields, atmospheric dynamics models of high-energy circulation systems. All of these have been built and refined and debated using the 4-hour dataset as the observational anchor. The data is still being used. It is not exhausted, but it is finite, and the questions that have emerged from it are not. Every new theoretical result about ice giant atmospheres or magnetic fields generates a prediction that cannot be tested against Neptune data because the data to test it does not exist. The gap between theoretical development and observational confirmation at Neptune is growing, not shrinking, because theoretical tools continue to improve while the observational dataset remains frozen at 1989. A return mission would not simply add to the existing dataset. It would transform the context in which that dataset is understood. Voyager's measurements of wind speed, magnetic field, and thermal output would be reinterpreted in light of sustained observations that characterize the variability, the seasonal cycle, and the spatial structure of each phenomenon. The 1,200 kilometers per hour would acquire a context. Does it vary by 10% over Neptune's 165-year orbit? By 30%? By more? The magnetic field tilt of 47 degrees would be understood as one phase of a dynamic system rather than a static measurement. The heat output would be mapped spatially rather than averaged globally. That reinterpretation is what sustained observation produces. That is what 4 hours cannot provide, and what the planet has been waiting for. Go back to where we started, August 1989. A spacecraft at 61,000 kilometres per hour. 4 hours. The reading, 1/500 kilometres per hour, sustained, planet-wide, on a world that should be nearly still. That reading has not been updated. Right now, as you settle into quiet, Neptune's jet streams are moving at 1,500 kilometres per hour, the same speed Voyager measured. The magnetic field is still tilted 47 degrees off axis, still generated from somewhere inside the planet that no instrument has directly sampled. Somewhere in that deep blue atmosphere, a dark spot is forming or dissolving, or has already formed and dissolved in the time since Hubble last looked closely. Triton is still falling, by an amount unmeasurable in any human lifetime, on a path that ends in a ring system billions of years from now. None of this has changed because we know about it. Neptune does not register our models. It was running at 1,500 kilometres per hour before Voyager arrived, and it will be running at 1,500 kilometres per hour when the next mission finally reaches it, after another long crossing of the distance between here and there. What has changed is what you carry. You know that the energy driving those winds is 4.5 billion years old. You know that the storms Neptune builds are too large to be permanent and too brief to watch. You know that the magnetic field follows rules that are still being written. You know that the largest moon arrived through violence, destroyed what came before it, and is now falling toward a dissolution that will build something new from its wreckage. All of that from 4 hours. 4 hours out of the 4.5 billion years Neptune has been running. The chaos was always there. The silence since 1989 is hours. The wind is still running. It has been running for 4.5 billion years. It will be running when we finally go back